All right, friends and neighbors, welcome back and Happy New Year. I think we're going to try with this video to close out sort of the IPERF discussion and our look at, or maybe our more in-depth look at TCP and UDP. So we'll do UDP today, but we'll do it in the context of YouTube and IPERF. So here we go. Okay, what do we already know or what do we remember about UDP or the User Datagram Protocol? Well, we know that it's RFC 768. We know that it's been around a long time and that its primary purpose was to provide a datagram mode of communication at layer 4. So this is unlike TCP, right? We're not going to do any handshakes. We're not going to keep track of the byte stream along the way. We don't have an algorithm for calculating bits in flight. It primarily has two uses. We have the command and response sort of thing. So can I have this? Sure. Or here's my question. Here's the answer. And so we see that all the time in things like DNS, Domain Name Service, DHCP or Dynamic Host Configuration Protocol, SNMP, Simple Network Management Protocol, NetBIOS. We see it all kinds of places. Okay, but we also see the use of UDP in all of our real-time streams. Why? Because we don't want to keep track of lost packets. We don't want to worry about trying to recover lost data or asking for it again. We're not worried about any of that stuff. And so for VoIP, for video, for gaming, these are all the things that we also use UDP for, or for which we also use UDP. We also know that UDP is largely unchanged since 1980. Now, that's not to say there haven't been some changes, right? There's UDP Lite, and as we'll see later on in this video, there's a completely new protocol that we use with UDP. Okay, so without further ado, let's take a look at some of the action in UDP. And for that, first thing we're going to do is IPERF. So I've got a server running on my host machine, and we'll go ahead and run an IPERF session. So you can see that I've been doing a little bit of testing with it here, and we'll get rid of, well, actually we need that for right now. All right. Now, this is completely different than the TCP test that we saw earlier. It's after different stuff, and for that reason it doesn't send as much data. It sends chunks of data because it's looking for some different ideas. And so what we can see here is we've got this output, right? It's sending 128 kilobytes, okay, so not a lot, at 1 megabit per second. This is an internal transfer, so it's from a VM to a host. We know that this capacity is way below what the actual capacity is. We also take a look at the number of datagrams, very small. So what is it actually after? Well, we're after jitter. That's the big one here. And so jitter is the difference between expected and actual delay. And what that does is gives us a measurement of application performance. Okay, so let's take a look here. Now I actually did two packet captures with IPERF here, and I want to show you the first one, the one that predated the one that I just showed you. Okay, so the significant difference here is that in this particular packet capture, I let IPERF do its own thing by default. And so we see this TCP handshake. So whether or not we're doing UDP, we're going to see initially that we're going to do a TCP-based connection. And so if we take a look here, right, we have the SYN-ACK ACK, that's our familiar TCP handshake, and then we have the IPERF specific communication. This is the things that IPERF is communicating between the client and server, right, the options for this particular transmission. And then right down here, we see that IPERF is establishing a UDP connection. And so this is our indication that IPERF is communicating those parameters between the client and server. Now, something else to pay attention to. Why are the source and destination both 43? Well, that's because I'm communicating with myself, and the VM is sitting behind the NAT connection for my hypervisor. And the hypervisor is this machine. So don't let that throw you. That's just the virtualization part of this. But one other thing that's kind of fun here is that we've got Wireshark recognizing that this is IPERF 3. Well, how does it know that? Well, right here we see 5201, and that's why it becomes important for us to realize that this is the default settings. So because it's 5201, that is actually a port that is used by IPERF on a regular basis. And so the dissector for Wireshark, the thing that tells Wireshark how to decode this, sees this particular port and says, oh, you are probably doing IPERF. Now that doesn't mean that whenever you see this, it's automatically IPERF. That's just what Wireshark is assuming. Okay, so we're going to scroll down here and we're going to see that we've got all of this IPERF traffic. We've got 1460 is the length of the header here, or the length of the data after the header. And let's take a quick look at our encapsulation. Well, we've got our IPv4 and there's UDP. So that tells us that we're in the middle of a UDP test. We've got an IPERF speed test header here, and then we've got data. So the headers are what reduces our overall capability. Now, the UDP header is actually pretty straightforward, right? It's just 8 bytes. So we get the source and destination, and then we get a length, and then we get a header checksum. So just 8 bytes. But the important thing to realize is that even though we're not doing TCP, we are still talking about a client-server connection. So this is still source and destination IP address, source and destination port numbers. Then we've got an IPERF header. This entire thing is not the IPERF header. We've got data after that. So the header is actually this part right here. So maybe we can see it by taking a look here, right? We've got a good size header, and that explains our 1460 payload. Okay, so we've got this guy here, right, our 12-byte header. All right, and so that continues, and we can see that we have the IPERF datagrams. But if we take a look here, maybe down here, the total number, you probably might not be able to see this in the video, but it's 939 packets total. Now that is dwarfed by the TCP test that we did in the previous videos. This is actually a very, very small number of packets. And the reason for that is that we're not actually after a capacity test. This is not a bandwidth test. The primary concern here is jitter. Now, let me open up the capture that we just did, and we'll see the difference here. So here is, you saw, well, maybe I'll go back and show you the settings that we used. So if I just up arrow here, we can see there's IPERF3-U. That is what makes it UDP test. And then we're a client, and then we've got the destination IP address. And then -P, well, that's the port number. Notice that I set the port to 10,000. Well, why did I do that? Well, we wanted to see the impact on Wireshark just changing the port number. So we can see, whoops. We can see there's our SYN/ACK, right? So this is TCP. This is the TCP handshake. Still the same IP addresses. And we can see this negotiation down here, and then we move into the UDP test again. But what's missing here? Suddenly doesn't know what the protocol is. And that's because simply moving off the port confuses the dissector, because we're expecting 5201. So that's really the only reason that I did this. We can see down here we've got a couple of more packets because I left it running a little bit longer. There we have it. It's actually a very, very small number of packets compared to TCP. We've got a whole bunch of extra stuff here that's in this capture because, well, I left it running. Okay, so this actually is a capture of, I think, 2 tests that we did. All right, so to recap what we did there, 2 IPERF3 captures, one with the default setting, one with changing the port. We see that it starts off as a TCP connection, and then it moves off into UDP, and we see a far fewer number of packets because the purpose is different. Again, starting off TCP, we move it to UDP, we change the port numbers, suddenly Wireshark is confused. So this is another look at UDP output from IPERF. We can see that we're worried about jitter. Now, what does this mean? This is 0.3 milliseconds. That's actually not bad. We don't actually start to worry about jitter until we get about 5 milliseconds. Jitter is one of the reasons that we do buffering. And so when you've got a lot of jitter or excessive jitter, then buffering sort of cleans that out, right? We buffer in a couple of packets before we start to play whatever the stream is. Now, this is not a big deal if we're talking about DHCP or DNS, who cares? But what is interesting is that when we run into real-time applications, then we are far more worried about the behavior. And those real-time applications, that's where we're going to see the need to do some buffering. Now, when you've got low numbers of jitter, well, this doesn't really matter. It doesn't really affect what we're doing here. And again, jitter is the difference between expected and actual arrival time. Well, let's do something else. Let's do a capture now, and let's see what happens when I go to YouTube. So we're just capturing here, and you can see that not much is happening. Right, we just got some baby packets here, but watch what happens when I open up YouTube. Okay, a lot of stuff happens here. We're all of a sudden at 2,000 packets, 3,000, 4,000, a lot of stuff happening. And we'll just start to play, oh, I don't know, we'll play some music here. Probably get an ad first. Okay, I think that'll do it. So let's stop this capture. And what I want to do is we'll go all the way to the top here to that first connection. And maybe what we're looking for first, so we went to YouTube, but how do we know how to get to YouTube? Well, this gives us an opportunity to take a look at some of the other traffic that might use UDP. Okay, it took me a second, but we can see we've got a lot of DNS traffic here, and it's going to Google, right? Google has a tie to YouTube. But what I'm after is the DNS query for YouTube. And so here is my machine, right? We saw that from the earlier captures, and I'm asking my gateway a little bit about YouTube. All right, so this is a standard DNS query, and we can see that this is wrapped up in UDP. So this is the command and response thing. DNS uses port 53, and here is my query. Please tell me a little bit about YouTube. So in the next packet, or a little ways down there, a couple of packets later, we see the response from the name server, and it says, well, here's your answer. So again, UDP, and here are a whole bunch of answers. You can see that the IP addresses came back. We'll just open one of them. And we can see that the original query was about YouTube, and here are the answers for YouTube. So for the purposes of this video, really what we're going to get out of this is take a look at all of these addresses that are 172.217.13. So all of these are associated with YouTube. So these are answers that I got back from my name server that will give me access to YouTube. And so now all of my conversations are going to be really with these IP addresses here. So this is packet about 4,000 or so. So if I go just a little below that, what do I see? Here's the conversation with those 172.217.13 addresses. And what is happening here? This is using the QUIC protocol, also in UDP. Now we just got done looking at IPERF doing a UDP test, okay? We know that DNS uses UDP, and we know that YouTube is all about pulling video, right? One-way direction video. So what this is telling us is that the data coming from YouTube is wrapped up in UDP packets. But we've got something else happening here. If we were looking at very traditional video streams or very traditional voice streams, we would expect to see other protocols there, like RTP. Well, what we're seeing here is a protocol that's there to support streams. And so this entire set of packets from YouTube is all about being wrapped up in this QUIC protocol. Is it a huge header? Does it really create problems for us? Well, it's not overly large. We can see if we pull this up a little bit here. Maybe what I'll do is this part of the header there, it's not enormous, right? It starts to compete a little bit with maybe TCP, right? Because TCP is 20 bytes compared to UDP's 8. Here we have some larger payloads, right? This is the payload here is 1,300 bytes. So all of the details, right, again, still from 172.217.13, you really got to pay close attention to that when you're looking at these captures, right? What was the request that you made, and where is the traffic actually coming from? What is actually being used? All right, so the real question for us now is, what is this QUIC protocol doing here in my UDP stream? We can also see that it's from the IETF, right, the Internet Engineering Task Force. Okay, so what is QUIC? Well, the title from the RFC is a UDP-based multiplexed and secure transport. So, wrapped up in UDP, we have this protocol, and the whole point is to have some form of transport services for the UDP-based streams that we're dealing with. And that's really the key. It's all about the streams. So, from the RFC, QUIC provides applications with flow-controlled streams for structured communication, low latency connection establishment, and network path migration. So this is about figuring out how to get your flows to you. Now, a flow and a stream, similar use. The terminology that we have, a flow is a set of packets going between the same source and destination. Usually, more commonly, we might even say the same source and destination IP address, same source and destination port, same protocol. But really, it's all about a set of packets going in a particular direction. And if you're accessing a stream, then you're accessing a flow that's heading from, in this case, YouTube to you. So it includes security measures that ensure confidentiality, integrity, availability in a range of deployment circumstances. So we saw that that was actually an encrypted payload that we couldn't see. And so really, again, this is about services for these streams, including things like what happens if we have to change the network path or establish a network path, and then deal with connectivity issues. So it's really all about handling the streams. Now, if you look at the QUIC RFC, dated 2021, it's actually a good size RFC. And so there are a lot of features and functions available with QUIC, but we see this as one of the major protocols deployed for streaming. So starting up a stream, getting access to the stream, managing all the network parameters associated with the stream, and then finally terminating that stream. So here is a quick look at some of the packets that are associated with a stream startup. And so this is a quick look at QUIC, right? And we see that we've got this initial conversation. Tell me a little bit about this. Oh my goodness, a handshake and then into protected payloads. So that is very reminiscent of TCP, but this is specific to streams. And so there are some other details associated with streams, things that we worry about that we don't always worry about with TCP. Now that sounds a little weird, but TCP is very concerned with ensuring that all of the data gets there. Well, streams are worried about getting most of the data there, but what we're really concerned with is performance and network migration and things of that sort. Getting access to a particular stream and then terminating that stream when we're done, but handling all of the details associated with real-time flow, not just whether or not your data got there. So these handshakes are a little bit different. Well, there we have it, friends and neighbors. This has been a sort of a walk down memory lane, right? A reminder about what UDP is, what its use is, but then we took a look at specific instances of UDP use in YouTube and IPERF. And then we've got this sort of brand new RFC, right? RFC 9000, the QUIC protocol. So we saw that IPERF UDP is really about jitter. So it's a different measurement. It's not about bandwidth or capacity or throughput. It's very few packets when compared to TCP. And really it's about measuring what's happening when we're going from source to destination for those packets, not how many packets can we push. And then, of course, all about the streams. Well, thanks for watching. Thanks for listening. Like and subscribe if I helped, and may those packets always reach their destinations, whether they're part of a flow or a stream or just a command and response.